All right, and this final chapter for Chem 111 has to do with chemical bonding, and in particular, what the actual shapes of molecules are and how to predict them. First, let's review a little bit of the vocabulary regarding the Lewis structure. So most of the time when we were doing Lewis structures, we had something that had a central atom, and for water, that's oxygen. It has these dots, these four dots around it are lone pairs of electrons. The lines that connect the hydrogens and the oxygens are single bonds. Those single bonds we can also call bonding pairs if we want. And then the hydrogens here are terminal atoms. A terminal atom is only connected to one other atom. A central atom is connected to two or more atoms. So first, let's talk about single atoms with central atoms with single bond pairs. And so something like this, beryllium difluoride, it's got two bonded atoms to it, and those two, the angle between those is exactly 180. It's a completely linear molecule. Then we've got something like BF3 that has three bonds to it, no lone pairs, and we get an angle of 120 as those go as far apart as possible. First, maybe kind of weird shape is tetrahedral. The central atom is right here, and then these green atoms, these fluorides, are the fluorine-carbon-fluorine bond is 109.5 between those. And you can also visualize it within this little pyramid that's given here, the central atom in the middle, and then the fluorines on the corners of the pyramid. Next one is called a trigonal bipyramid. It's two pyramids fused together through the bottom. And it's got a couple of different angles in it. It has this angle right here of 90 degrees, and then within this plane, the angle is 120 degrees. An example of molecule for that is PF5. And then finally, SF6 has an octahedral arrangement, where the six bonded atoms are at the corners of an octahedron. It's a prism sort of shaped like this. Well, we face, still to this day, the problem of trying to render three-dimensional objects in two dimensions, and this is the best that we've come up with so far, is this dashed line method for doing this. So take this, we'll say this is CH4 that we have here, and so this hydrogen is that hydrogen, this hydrogen is that hydrogen, carbon, of course, is the carbon. And then the question is, we have this hydrogen that is actually in a three-dimensional structure would be coming out of the screen towards you. In a 3D structure, this one would be behind the screen. So this carbon, this hydrogen, these three are all in the plane of the screen, whereas this one comes out and that one goes back. We render the one that goes back with the dashed line to show that it's receding, and we have the one that's coming out at you here as a bold line with a wedge. We call this a wedge and this a dash. Here's all of the structures of the various types that you would need to know, all 15 of these. And let's take, for example, this tetrahedral structure. So if we have a central atom with four atoms bound to it, bonded to it, then we just call it just tetrahedral. If we have something like this, could be NH3 that we have here, a nitrogen, and then hydrogen, hydrogen, hydrogen with a lone pair. Well, the lone pair occupies one of these sites now. So the electronic geometry is tetrahedral. But once we cover up this lone pair and look at what's left, the nitrogen, hydrogen, 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 this is a trigonal pyramid that's left. And then now we could have something like water, where the E is O. We have an oxygen here, hydrogen, hydrogen, lone pair, lone pair. The electronic geometry, again, is tetrahedral. It is for everything in this row. But the molecular geometry, where we look only at the placement of the atoms, oxygen in the middle, hydrogen, hydrogen, is bent, or it also can be called angular. Well, once we know molecular shapes, we can do some things with them, and let's review for just a second. In chapter 9, we talked about this dipole. When we have, for example, here hydrogen bound to iodine, there's a positive charge that develops on the hydrogen, there's a negative charge that develops on the iodine, and this acts as a tiny magnet. Also, from the previous chapter, let's talk about electronegativity, and that's the ability of an atom in a bond to attract electrons to itself. Fluorine is the big shot here. It's the strongest. It has the highest electronegativity. In general, as we go away from fluorine, either to the left or down, then the electronegativity drops off. The one that's really weird as far as the trend is hydrogen. Hydrogen should fall somewhere here between boron and carbon. But we can use this to tell how polar a bond is. We have a large difference in electronegativity, like for example between carbon and fluorine. Then there's the bond is very polar between the two. Okay, and as long as we're just talking about two atoms, then it's simple. If the atoms are the same, then it is nonpolar. If the atoms are different, then it's polar. We use this notation here where we have this arrow, and the arrow has, this is to represent the positively charged atom, this little cross here on the end, and then this arrow points from the positively charged atom to the negatively charged atom. Okay, and the negatively charged atom will be the one that has the higher electronegativity, which of course is fluorine when it's bound to anything else. All right, well, let's see how what it takes for a molecule to be polar. It has to have polar bonds, and it has to have an electron density that's distributed unevenly. So let's see what that means. Well, CO2 is nonpolar. It's a nonpolar molecule, and it has two very polar bonds in it. So carbon and oxygen have a big difference in electronegativity, and so this bond is polar, and this bond is polar. However, the polarity is equal and opposite, and so the amount of polarity that goes to the left is equal to the right, and so there's no net dipole. The two little dipoles cancel each other out. However, if we have something like water, the oxygen is much more electronegative than the hydrogen, so polar bond, they're both pointing in a middle sort of direction, but they're also both pointing up. And so while part of this dipole cancels this dipole, net, there is a motion, a dipole up. So we're left with a pretty large dipole for water. All right, next let's talk about molecular orbital theory, and we can talk about bond order. And here's a molecular orbital diagram for He2. So if we were to try to take two helium atoms and put them together, we would have 2 electrons in a bonding molecular orbital and 2 electrons in an anti-bonding molecular orbital. And so the bond order would be equal to 1/2 times 2 minus 1/2 times 2, so 0. So the bond order between those two would be 0. Bonds with large bond orders are predicted to be short and strong. Bonds with small bond orders are predicted to be long and weak. There's also some terminology that we should talk about. So this is a molecular orbital diagram for dilithium. And dilithium has a total of 6 valence electrons. Excuse me, 6 total electrons. Each lithium has 3, so 3 times 2 gives me 6. 1, 2, 3, 4, 5, 6. We have, in this diagram, this empty box is the lowest unoccupied molecular orbital. And that's always right next door to the highest occupied molecular orbital. So I go up, till I hit the highest molecular orbital that has electrons in it, and that is the highest occupied molecular orbital. And then the one right next door to that is the lowest unoccupied molecular orbital. Okay, and then we can go beyond that to some more complicated species. So something like diboron. Each boron, the way this is constructed, it's only valence electrons. So diboron has 6 total valence electrons, and we go 1, 2, 3, 4, 5, 6. And then as we go to atoms that have more and more electrons, dicarbon, 7, 8, 9, 10, and among the ones we've talked about, the highest bond order here is N2. N2 has a triple bond between the two because it has 2, 4, 6, 8 electrons in bonding orbitals, and it has 2 in an antibonding. So 8 times 2 is 6. 6 divided by 2 is 3. This one has a bond order of 3. And then we go on, we put more electrons in. For O2, we start to fill this antibonding level. So electrons now go into an antibonding level, and so the bond order goes down. And then when we go to F2, we add 2 more electrons to an antibonding level, and so that has the lowest bond order of all. All right, and then finally we should talk about whether once they're filled, they are paramagnetic or diamagnetic. In order to be diamagnetic, we have to have all paired electrons. And so diboron has 2 unpaired electrons, so it's paramagnetic. Dicarbon has all paired electrons, paired, so it's diamagnetic. N2, all the electrons are paired, so it's diamagnetic. O2 is an interesting case. It is paramagnetic because these 2 electrons, the lowest energy arrangement is up. That gives us net 2 more up electrons than down electrons, and so it's paramagnetic. And then F2, with all the levels filled, is diamagnetic.